Welcome to Higher Structures seminar series of Feza Gürsey Center for Physics and Mathematics. Today our speaker is Oliver Lorscheid from University of Groningen, and he will tell us about zeta and k in F1 geometry. We thank Oliver for giving this talk, and please, Oliver, yeah.
Yeah, thank you very much for this invitation, and it's a pleasure to talk about it. We'll talk about some work I've done mainly many years in the past when I was a young postdoc, and there were some recent development on K-theory recently that I mentioned at the end. But I tried this talk just to give a gentle overview of these topics, and at some point I really want to introduce you to some variation or one F1 geometry, one approach, which is a bit more technical, but the rest I hope is lighthearted and concentrates on surveying the ideas. I have here a secondary screen where the slides, so I will look away from the camera. Yeah, and please, you should interrupt me with questions. So it's all about communicating these ideas, and I'm happy if you ask when something is not clear. And I spent rather some more time explaining one thing than covering all the slides, which is not necessary. Okay, so let's start in the beginning. I want to start with a short history of F1 and present the main ideas that are there without going into much depth, since I want to talk later about two different topics, so I have some time. The first person who advocated this idea of a field with one element, or he said a field of characteristic one at the time, was Jacques Tietz in the 1950s. So there's one paper which contains these ideas from 56, and he gave several talks, as I heard from colleagues at the time, like Pierre Cartier, that he studied the analogy of algebraic linear groups over finite fields and the symmetric group. And they acted, well, this algebraic groups acts on Grassmannians or flag varieties more generally, and Sn acts on something like k subsets of n. So let me one moment. I have to activate this here, and it's a good color, maybe orange. So I put up this picture. We have here GLN acting on a Grassmannian over finite field, and on the other side, combinatorial analog of Sn acting on k subsets of n. And just give me a moment because I forgot to do one thing. Can increase the pointer a little bit. Oh, this is coming up. Okay, sorry, I don't find the option. We will manage without, so I will mark up some things. So this analogy between these two things is mainly in terms of counting polynomials. So we can count points in the Grassmannians, and the number of points is a polynomial in Q. And if we take Q goes to 1, we find the cardinality of the collection of k subsets of an n element sets. And similar for points of GLN, if we take the limit Q goes to 1, where we have to resolve some 0 because there's factor of Q minus 1 to the n, then we get the number of elements in Sn. So it's an analogy of some group actions which have invariants counted in Q, and the limit Q goes to 1 counts things on the combinatorial side. So this led him to the conclusion that SL should have an algebraic geometry interpretation as the general linear group over F1, And this collection of K-subsets of an n-element sets should have an algebraic geometry interpretation of a Grassmannian over F1. And well, if you go back to the year where he advocates this mid-50s, this was totally crazy. This was 10 years before Grothendieck came up with this revolutionary definition of a scheme. At that time, people, André Weil introduced varieties over fields that are not algebraically closed, which was top notch. And something like talking about the geometry over fields that doesn't exist. I mean, according to Pierre Cartier, who thought this, people would not take him serious on that, or I mean, nobody was working on that. These ideas were kind of dormant for 30 years until in the 80s, Smirnov talked about Alexander Smirnov, so there are many Smirnovs. He talked about arithmetic applications of F1, and this was later written down up by Yuri Manin in the early 90s. And they used looked at a different analogy. So if we have a curve or projective smooth variety over FQ, then we know very well what the zeta function is of this variety. And Andrew Weil and then later Pierre Deligne used the algebraic geometry of this curve to prove the Riemann hypothesis for the zeta function. The Riemann hypothesis for the zeta function of spec Z, this is still one of the wide open central problems. And Smirnov's idea, which then entered Manin's lecture notes on the topic, we're imagining that we maybe can copy the situation that acts the curve over FQ by saying spec Z, or more concretely, the one-point completion of spec Z, including an infinite prime, should be a curve over this elusive field with one element. And then developing a geometry of that might eventually lead to a proof of the Riemann hypothesis. And this idea gained a lot of attention, and all of a sudden people were seriously looking into this idea of F1 geometry. And there are people nowadays still working on it, most prominently Con Consani, who have a body of work of probably it's ranged into the thousands of pages now, developing theories for that. Yeah, they're highly active, but there are also other approaches, other people. There was Durov. Shai Haran has a lot of work in this direction. We're aiming at this arithmetic application. There were a few other less prominent applications in this direction. There's an unpublished preprint by Smirnov and Kapranov explaining how this relates to knot theory, to reciprocity laws. There's a paper by Alexander Smirnov on how one could prove the ABC conjecture by Hurwitz's theorem for P1 over F1. So there's a large pool of ideas. The Riemann hypothesis is the one that was most popular at the time. You have to say, disclaimer, I think none of these arithmetic applications are realized up to date. This combinatorial ideas of Jacques are understood nowadays. I mean, this is also where my own work focuses mainly on. And so this is the pool of ideas that gave rise to birth of F1 geometry. And the first person was bold enough to give a definition of what a variety over F1 is Christophe Solé. And his intuition stemmed from Arakelov geometry. So, I mean, he's very much in this picture of arithmetic applications, but yet this picture of that geometry at the infinite prime should be governed by complex differential geometry. So his definition, yeah, was the first step, but nowadays I think, I mean, nobody really worked on that, but it gave ideas for further developments. So I can move this away, good. So in his paper where he gives this definition, one finds two more ideas which are important and which are actually the topics of today's talk. So coincidentally, it's in a paper of 2004, but he talked about it already in the 90s. So I don't know precisely. There's some slides of his from 96 or something, but it's published much later. And he introduced a zeta function for F1 schemes, but these are finite type schemes. Spec Z should be something like an infinite type scheme because we have infinitely many primes. It's something much more difficult from the F1 perspective. And he talked about K-theory. He addresses this to Manin, but there's no trace in the literature. Um, and the idea is, well, K-theory has many definitions, but one of the definitions is that this is the homotopy group, I mean, Ki of some field, and here we apply this to the field with one element, is a homotopy group of the classifying space, this is this B, of GL infinity of our field F1, and then, well, we use the plus, there's an extra base point that we add. So we could try this definition. But this GL infinity of F1 is something that we just write down. It's not defined, but if you remember in the last slide, we talked about GLN F1 according to Jacques Titt. So let's play this through. GL infinity of F1 is just the union of finest GLNs where we always embed GL and GLN plus 1 as kind of upper block matrix and attach ones. And it's just a union. So these are matrices which are identity matrices up to finitely many coefficients which are not one, which are differ from the identity matrix. And then here we have this term GLN of F1, which according to Tietz philosophy should be a symmetric group. So if a union of symmetric groups, finite symmetric groups, and this is something that we call S infinity. So it's a permutation on infinitely many elements, which fixes all but finitely many elements. An element of
I
this.
have a question.
Yes.
Up to now, are you stating properties that if F1 exists, it should satisfy, or are
Yeah.
you using a definition of F1?
Now, this is philosophy. You see, there's a color code here, right? The red
Mhm.
parts is something that's not defined. That's just what we would like to think of.
Okay.
And the black
Mhm.
parts are things that make sense.
Mhm.
So, I mean, I'm starting with K, what it is. I'd say, well, we would like to find like this, but doesn't make sense. And then I'm going through, we want to make sense of that. And this GL infinity, well, it should be something like that, but the GLN of F1 is still not defined. But now here comes in black a definition that makes sense. Does this make sense to you?
Yeah, yeah. Mhm.
Yeah. Okay, so I mean, this S infinity, this is something well defined. These are, as I said, permutations of the integers which fix all but finitely many. Um, let's say positive integers. And then we can here to this S infinity, to this group, we can apply the plus construction. So we add a base point, take the classifying space, and study the homotopy groups of that. So this is well defined, and this appears actually in the Barrett-Pretty-Quillen theorem, and it identifies this with the stable homotopy groups of the sphere. So, I mean, the only thing that makes sense here is this here, which is a theorem from homotopy theory. And this philosophy says, well, whatever K of F1 is, if we can define it, it should be the stable homotopy group of the sphere. Stable homotopy group of the sphere. Okay, so this is just a formula that Soleil wrote down, which should hold if we have a good K-theory. And that's the second topic of today. So I will talk about these two things. First, zeta functions and K-theory. Okay, any further questions here, or shall we start with zeta functions? Okay, then let's go ahead. So here's Soleil's definition of a zeta function. And this definition actually doesn't depend on our definition of F1 variety. So you can choose your favorite approach to F1 geometry if you have one, or you just believe me that there is some approach. And we say X is an F1 variety, whatever this is. The important thing is what we learned from this idea of the Riemann zeta function is that Z should be something like an algebra over F1. In particular, there should be a base extension. If we have our F1 scheme X, there should be a base extension to Z, which is, you can think of it as X tensor Z over F1. So that's typically a feature of any F1 geometry that's on the market. I think literally every geometry. But for now, we just require, we have such a theory and we can talk about the scheme XZ. And the definition of the zeta function only depends on the scheme. So we can forget about this X if we wanted. And then the requirement is that this XZ has a counting polynomial with integer coefficients. So there's certain coefficients AI. And this polynomial counts the number of FQ points. So here's one example below. If XZ is a projective line, we know what are the FQ points. They're Q plus 1. So the counting polynomial is just T plus 1. And this should hold for all prime numbers, prime powers, Q. Okay, so once we have this counting function, we can make sense of the zeta function over F1. Namely, we first look at the zeta function over FQ, which I write as zeta x of Q and S, because now I want to vary Q and look at this as a function in Q and in S. Well, we know very well the zeta function of x over FQ. It's just exponential of the infinite series where we take points over FQ to the R. So we just count points with our counting polynomials times Q to the minus RS over R. And one observation that's easy to see if you look at this exponential series is that if you consider the zeta function as a function in Q, then it has a pole at Q equals 1 of order nx of 1. Or, I mean, it has a 0 of order minus nx to 1, however you want to read that. So if we now want to look at the zeta function of F1, I want to take the limit Q goes to 1. And I'm talking about this pole because we first have to resolve it so that we can take the limit. And that's precisely what we're gonna do. Zeta function of our F1 variety X is simply the limit Q goes to 1 of zeta x Q S, where we resolve the pole. So this is Soleil's definition. And it proves that this is actually equal simply to a product. I range from 0 to n. N is the dimension of xz over z. Of terms s minus 1 to the power ai, where ai are the coefficients of our counting polynomial. So it's nothing deep. It's you look at the series and you just play a little bit around with that and you get there. Here's an example, just an interesting real life example. We can take the Grassmannian 2,4, which is not a projective space, so it has an interesting counting polynomial. So the FQ points, they're given, I mean, one way to compute it is they're given by the Q factorial 4/2, which by definition is this ratio here. And if you multiply things out, you see this polynomial. Another way to get to this polynomial directly is to take Schubert decomposition in affine spaces and count the corresponding points. And then you see, well, in dimension 2, you have 2 Schubert cells, 2 A2s, and in other dimension, you have 1 Schubert cell, and then you get the corresponding coefficients here. So it's a different way if you know which types of Schubert cells you're. Anyways, the Grassmannian has a polynomial count, and then using Soulé's result, this means that the zeta function of the Grassmannian 2,4 is a product over these factors here. And if I multiply them out, we get this degree 6 polynomial in S as the zeta function. Okay, this was just one example of a zeta function. There are two observations, which does follow directly from the definition and these results that we have. First of all, zeta function is rational in S. In our example, we have polynomial, but the AIs could be negative. So it's a rational function, which is an analogy to what happens over finite fields, except it's not rational in Q to the minus S, but S. So there's kind of a difference here. And the other thing is that the zeros and poles of the zeta functions are totally clear from this description. So zeros and poles occur at S equals to I, and the order is the AI. So, I mean, the question about the Riemann hypothesis here is trivial from this form. The only thing that's not totally obvious, and which was my contribution to the topic, is a functional equation, which actually uses some heavy machinery, but is very easily deductible from that. Namely, if X is smooth projective irreducible in dimension n, actually just has to be this over F, the base change to a FP bar. Then we have this functional equation. Well, the dimension is n, so zeta x of n minus s is equal to zeta x of s times the sign, and the sign is -1 to the nx of 1. Okay, I show you the proof because it's very easy and but shows what we need for that, namely the well conjectures. So I define BI as the Ice-Betti number of L-adic cohomology of X over FP bar. And then under the given assumptions, I can use the well conjectures, which basically implies here, well, the variety is pure and the counting polynomials are precisely the Betti, the coefficients of the counting polynomial are precisely the Betti numbers. I mean, I'm assuming this counting polynomial exists, of course. This is a standing assumption at the moment. Otherwise, this wouldn't be true. So the even Betti numbers occur in the counting polynomial. The odd Betti numbers are 0 because our variety is pure. And what I'm using, the other ingredients is Poincaré duality for, in this case, L-adic cohomology. And then I simply insert the Soulé's product decomposition of the zeta function and the Poincaré duality and kind of an elementary computation that I didn't write out here. It's a change of variables and switching S with n minus S identifies this product with -1 to the n of 1 times the product for the zeta function S. So I just use two big theorems here to deduce this. One observation, which I don't dwell on further, but which is also entering this whole philosophy, is that nx of 1, which should count the f1 rational points, is actually the Euler characteristic, because it's a sum over the b2i, and then I can re-enter the bi's because they're 0. So you see nx of 1 is really the Euler characteristic, in this case of aladic cohomology. But if the variety is smooth projective, say over the integers, we have this comparisons theorems of aladic cohomology with complex, say, de Rham cohomology or singular cohomology. And this would be equal to the Euler characteristic of the complex variety. So it doesn't matter which cohomology theory we use here. Okay, this is all I want to say about zeta functions over f1. So if you have questions on that, best speak up now. Okay, then let's jump to K-theory. I want to start with a short reminder on the Q construction, and I go a little quicker over that because it's a matter of time that I can talk about some interesting things. But I want to remind you how K-theory is set up. So if we have a K scheme and can think of K as your favorite field at the moment, later it will be F1. Then first we look at the category of vector bundles. And we know this category of vector bundles with, I mean, nowadays I think we would say model structure, but originally it was said this is a class of admissible monomorphisms and admissible epimorphisms, which are also in the categorical sense called normal and monos and epis. So a monomorphism of vector bundles S to E is admissible if it's a kernel of its co-kernel. For vector bundles, this how do I say this? I mean, for modules, if you map Z to Z, you cannot, the map multiplication by 2 would not be admissible, for example. This would be one counterexample. And an epimorphism is admissible if it's a co-kernel of its kernel, dually, and every epimorphism of vector bundles is actually admissible. So this is not a problem. In F1 geometry, there we have a restriction. This will be a little bit different. And a remark is that iota is an admissible monomorphism. Well, if it's a kernel of its co-kernel, so we can say pi is a co-kernel of iota, and we get short exact sequence. And conversely, if we have pi an epimorphism, we can, then it's admissible if we can complete it with iota to a short exact sequence. So that's a different way of looking at it. The admissible monos and epis are precisely the monos and epis that appear in short exact sequence of vector bundles. By short exact here means as short exact as sheaves. And kernels and co-kernels, I didn't say this, but here it's written, are computed in the category of coherent sheaves, because otherwise they might not exist. Okay, so that's our setup. We have category with this class of admissible monos and epis. And then we can form a new category, Q bun X. This is a Q construction, which has the same objects, vector bundles over X, but morphisms are now diagrams like this. We have an admissible mono in the inverse direction from some intermediate object to E. And we have an admissible AP from S to F. So this means we are looking at subquotients. S is a sub-object, and then we take a quotient. and they're admissible in the sense that I explained. Well, and this is just up to isomorphism of S, so up to diagrams of this form. And then to form K-theory, well, we have the Q construction, then we take a classifying space, loop this out once, so we take the loop space, and finally take Ontp groups of the space. So it's kind of a horrible space that is super hard to compute, but that's Quillen's Q construction, which was a breakthrough in K-theory from previously Grothendieck groups and certain pi1, pi2 that existed for certain rings and fields. And yeah, that's the general theory. Okay, now our task is to apply this to F1 schemes and to make sense of K groups of F1 schemes X. And what I want to do now is to explain you one approach to F1 geometry, which is the simplest approach. Namely, we are monad schemes. But before I jump there, do you have questions on the Q construction, on K theory? Okay.
Maybe
Yes.
just I mean, I'm not all that familiar with everything. So, what's the sort of maybe intuition behind this construction and why one goes into this?
Okay. So, yeah, I'm maybe not the best person to ask about this developments in K theory, but I
Uh,
can give you a few motivational pointers. So there's on page 8. So let me go to a blank page at the end to scribble something. So there were this K0 groups of X, which is this is basically I mean that's a Grothendieck group. So we take direct sum Z over vector bundles. Modulo relations of the form class of E equals class of S plus class of Q if we have a short exact sequence of this form. So that's a Grothendieck group, which appeared in many contexts. I mean, this is very prominent Grothendieck's philosophy of creating a universal cohomology theory for varieties. So this is kind of fairly close to such a cohomology theory. It's the best that one can do, and the idea of motives derives from there. But so this K0 terms, the zeros parts, that they appear strongly in algebraic geometry. But then there were some definitions of K1 and I think of schemes probably, maybe rings. I'm not totally sure. Let me. I guess we can do this probably was probably for schemes. I'm not sure. And then there were case two Milnor case theory for field. Very small k. So there were some definitions, and the thing is that there was the beginning of a long exact sequence, which is called the localization sequence. If X is something like U together with Z, where this is open and this is closed, then there was a sequence K0 of, I believe U is here, K0 of X, K0 of Z, and then we would have the K1 terms of U K1 of X, and so forth. So there was a beginning. I'm not 100% sure how much of that existed before Quinn came on the ground, but there was a question how to continue that. And Quinn's K-theory was doing that. So, I mean, that's maybe one way to yeah, to motivate that. I don't know if it's really the historical motivation and the only one. There are also, I mean, another relevance of K-theory. I don't know if Elian knows this better. I'm not the most arithmetically minded person here, but there are very intimate relations between values of zeta functions and high K-theory of the number field, and also conjectures about that, like the Lichtenbaum conjecture, which I think appeared only later when K-theory already was defined. I'm not totally sure about this history. So there are certain relevance of deep arithmetic problems, which I don't really understand, so I cannot tell you more about that.
Okay.
Does this somehow
It gives some picture.
a little
I mean,
bit?
thank you
Yeah.
for taking the time to explain.
Okay. So let's now do something that I understand, which are monolith schemes. This is the simplest approach to F1 geometry, and actually the one where I studied K-theory in more detail, even though K-theory applies, you could, as soon as you have a notion of vector bundles, you can apply K-theory. And I think most approaches to F1 geometry have natural notion of vector bundles. But still, this is the easiest notion, and it's somehow the intersection of all different approaches to F1. I mean, it appears as a sub-theory of any other more sophisticated theory. So let me stick to monolith schemes. And the idea is monolith schemes are something like toric varieties over F1. It's a little bit more general, but if you know toric varieties, you get intuition for that. So a toric variety is defined by a fan in Rn. Here's a picture of a fan. A fan consists of cones that are embedded in Rn, and these cones have a certain intersection behavior. So the cones on the boundary of a cone is again in the fan, and two cones intersect in cones in their boundaries. So they cannot overlap weirdly or something like that. This here would be the cone of P2, or the cone that defines P2. And the toric variety X sigma of this fan is defined as a co-limit of certain affine toric varieties f x small sigma. And co-limit means union, if you want. It's covered by this affine toric varieties, where x sigma k is the spectrum of this monoid algebra K adjoint A sigma, where A sigma is a monoid or semi-group given by all v's in z to the n of the dual cone. So dual cone means for every w in our cone sigma, v times w, the scalar product, is non-negative. And well, I wrote this is standard writing toward geometry chi to the v because we want to consider A sigma as a multiplicative subgroup while it's a subset semi-group, it's not a group. It's actually an additive subgroup of z to the n, but we write it multiplicatively to make sense of this monoid algebra. Because the semi-group operation here becomes the product of the monoid algebra. And then the idea is, well, over field, we take this spectrum, and over F1, we wouldn't take a monoid algebra, but we would just take this monoid itself. And we do something like a monoid spectrum. I write an M spec here to make clear that it's not the spectrum of a ring, but of a monoid. And then the monoid scheme of sigma or the toric variety of F1 is simply the co-limit of this affine monoid schemes, or co-limit union, as you want to call it. Okay, let me walk through now, and I try to do this. Yeah, this is a point where I want to ask with how much detail I should do that. These are maybe 5 slides. I can just browse quickly over it to give you an impression. It's not so important that you really digest this and that we go over all examples, but if you're motivated, I can spend some more time with that. Ilian, what do you think?
It's up to you. I mean, you can skim through quickly.
Yeah, then let me go a little quicker through that. Especially the geometric part. Maybe I emphasize the algebraic part a little more, because then we have a good idea of the affine picture. And then you maybe can believe that there's a gluing process to glue affine things to some more geometric thing. So one twist that's kind of important for F1 geometry is that we don't only take monoids, but we add base points to the monoids, which means I talk about pointed monoids, which is, well, all my monoids are always commutative, so I will not mention that again. And they come with an extra element 0, which multiplies everything to 0. And as a monoid, it has a unit, of course, 1. So these are monoids with 0 and 1. A morphism is simply a structure-preserving map. It's multiplicative and preserves the constants, which defines us the category of pointed monoids. So that's our category of algebraic objects. In usual schemes, we use rings. In F1 geometry, or this approach to F1, we use pointed monoids. Here are some examples. To start with, F1 in this series simply is a pointed monoid with 0 and 1, nothing else. And this is an initial object in the category. I mean, for every other point monoid, there's a unique morphism from F1 into this monoid, which maps 0 to 0, 1 to 1. Another first interesting example is the free algebra in T over F1. So it's somehow same as polynomial ring in the world of rings, but here it's not a ring, of course. This is 0 together with all monomials in T. So T to the I, where I is a non-negative integer. T to the 0 is 1, and then we have powers of T. And well, this is pointed monoid, as you see. And it really has kind of the categorical property of a free algebra. So every map of T into some other monoid extends uniquely to a monomorphism. Then another rich source of point monoids are rings, but just for getting addition. Every ring has a 0. I mean, rings is here in the algebraic geometry sense, commutative with 1. And so we get a monoid with 0 and 1. And this here has a left adjoint, the kind of a free functor. If we have point monoid, we can send it to a ring A plus, which is defined as we take the monoid algebra, the adjoint A that appeared before, but now we have a point monoid, so we have to identify the base point, which is 1 times 0, with a 0 in our ring. So we divide out this ideal, and as an abelian group, these are just linear combination, Z-linear combination of non-zero elements in A. And this free construction, this is what I mentioned also before. This is a base extension to Z. So if we have a monoid, we can base extend to Z, which is a ring. So this should be sort of our base extension from F1 to Z. This is not really a tensor product because we're changing categories, but it's an analysis operation that we want to use here. Okay. And now, so this is the algebra which is important. And now I just go quickly over that. If you want to, the next, want to define the spectrum of a monoid. And for that, we define what a prime ideal is. Well, it has this axiom, it contains 0, it multiplies elements in A to A, the complement's multiplicative set, like a usual prime ideal of a ring. We just skip this axiom that it's an additive group because we don't have any addition, so we just cancel that. There's something like a unit group. This comes later up again. So every monoid, the subset of invertible elements of monoid form an abelian group, which is called the unit group. And then there's a process of localization. This works as for rings. We just copy the same definition and we get a localization of monoids by which makes certain elements invertible. And especially we can this is a little strange here, I think. So A with, I want to define this monoid A joined A minus H minus 1 is a certain localization. And similarly, if we have a prime ideal, we can localize at this prime ideal. And we get the localization, complete analogy to rings. And then if we have set this up, we can define the monoid spectrum of A as a set of all prime ideals. Let's call it X, just to have a short letter. And this comes with the Zariski topology, which are opens UH of all prime ideals that do not contain the given element H. So the complement would be the zero set of H, which is Zariski closed. But topologies generated by opens, of course. And there's a sheaf in monoids, which is uniquely determined by the values on an open set UH. It's the localization of A in H. This is nonsense here. And the stalk in a prime ideal P, which is the point of our space, is the localization in P. So in total analogy to what we do when we define a scheme. So we just replace ring by monoid and use the construction from the previous slide. So in the end, the spectrum here is a topological space together with the sheaf in pointed monoids. And here's some examples. So let me do this quickly that you get a little bit of an impression. The topological space here tend to be finite. If our monoid is finitely generated as a monoid, then we only have finitely many prime ideals. And the first example is if we have a pointed group, so A is just units and 0, like F1, then we only have a 0 ideal. This is like the spectrum of a field, or every non-zero element is invertible. And then the base extension, I put down the base extension, this is something like Z joined, this is a group algebra here. The affine line, it's a spectrum F1 adjoint T, analogy to usual schemes, and it's justified by the base extension being the affine line over Z. And here we find two prime ideals, the 0 ideal, and then the ideal generated by T. There are no other ideals. I mean, T plus 1 doesn't exist. That would usually appear on the affine line over Z or over a field. A2 then has two variables, and we get four prime ideals like this. Something that is a little bit different is if we take the multiplicative group scheme. This would be we take F1 adjoint T, but we invert T. What's happening then is that T becomes invertible. So again, all elements are invertible. F1 joint T plus minus 1 is of this form like above, and the spectrum is just a point. So this is it's a one-dimensional scheme, but it only has a point, which is a little weird. This doesn't happen in usual algebraic geometry. But yeah. Okay, so these were a few examples. Let me now explain you finally what's a monoid scheme. Well, monoid scheme, it's topological space X together with a sheaf in monoids, such that's locally isomorphic to spectra of point monoids. So the same what you would do for schemes. The scheme's topological space with a sheaf in rings that's covered by spectra of rings. And there's a natural notion of morphism, which I don't go into. But to revisit the motivating example, if we have a fan of a toric variety in Rn, then now we would define A sigma as the Semmer group or monoids that I said before, but we add 0 because we want to work with pointed monoids. And then if we have an inclusion of cones, this gives rise to localization, to an open immersion of affine monoid schemes, which are the M specs of these guys. So we have monoid schemes which are open inside the other, and then our monoid scheme would be just the union of these opens, or categorically the co-limit. So this shows that toric varieties are a special case of monoid schemes, but our monoids that appear from a fan are of a very special type. So there are more general monoid schemes than toric varieties. They don't need to be finitely generated. They can have torsion. I mean, here we have submonoids of Z to the N. And there can be some other effects. Our monoid scheme can be non-separated. Something like the affine line with a double point is something that's defined over F1. Okay, so this is more or less, this is kind of the primary monoid schemes that I want to give. So once you set up the definition of your algebraic objects, which are point monoids, the rest is fairly straightforward. There are a few pitfalls where you have to be careful that everything works out. But basically, if you have the right definition in your hand, you just follow Hartron's chapter 2 or something, and you arrive at the definition of a monoid scheme. Now, to define K-theory, we want to talk about vector bundles, and I only explain them to you for affine monoid schemes where it's actually something modules over A. And well, they have different names depending on where you look. It could be a module over a monoid A or an A set, or sometimes they're called A acts because the monoid acts on something. Well, this in our setting, it's a pointed set M. So it has a base point, which are also called 0. So this comes up here. Base point is also just 0, together with an action of our monoid on M that satisfies the obvious axioms. So the constant 0 acts on every element of M by mapping it to 0. This is 0 in M, this is 0 in A. Didn't write this out. 1 is acting neutral, and any element fixes the base point of M. And then there's a associativity of the action, and that's an A set. What we are interested in are something like vector bundles, which are finally, well, I should say projective A sets, but up to, if we localize, so later in the geometric setting, we can take small opens, so it should be locally free. So let me just stick to free, not projective. An A set M is free if it's a co-product of copies of A. And the co-product in the category of pointed sets, or pointed A sets also, This is the one-point union, which is written topologically as a wedge product. So the one-point union, here's a picture. It identifies different copies of A at 0. So non-zero elements in different copies are distinct, but the zeros are identified. Okay? So that's a free A set. The rank is just the number of copies, n. And geometrically, if we have monoid scheme, a vector bundle of rank n, this is a sheaf of on X together with an action of OX in the sheaf sense. So for each open OX of U acts on E of U by an action as I defined before, and the condition that this is locally free. Like the definition of a vector bundle as a locally free sheaf. Okay? This makes sense. I mean, want to give you in the affine case, a proper definition, and then the vector bundle, this is, well, you just copy what you do in usual algebraic geometry. Okay, so now this is something now that where we copy the idea from before. We want to define admissible monoidal epis, or I use the word normal here because it's really the categorical characterization that normal mono is the kernel of its co-kernel. And this can be characterized if we have an A-equivalent morphism that's a mono or an epi, then this is a normal mono or an epi. Definition is here. If and only if, in the case of a mono, it's injective, no further restriction. So this is different from vector bundles where we had an additional restriction. And normal epi means it's surjective. And here we need an extra condition. The fibers of non-zero elements have not more than one element. It's surjective, so it has at least one, but it has exactly one element. Okay, here's an example of how you should think of that. If we have three A sets, the base point, this is a zero object. And then we embed into a free module A set of rank 1. This embeds into one factor of something of rank 2. And then this epimorphism contracts this orange part here to the base point, and the rest of the green part goes bijectively to the green part. So this would be an admissible exact sequence. And then for vector bundles, you generalize this by saying on affine patches, the restrictions have to be normal monos and epis, and you get there. Okay, so this gives us the structure of admissible monos and epis, and we can perform the Q construction that I explained in the beginning. These are the objects are vector bundles. The morphisms are admissible subquotients. So we take a normal subbundle S of E and a normal quotient Q, and we divide out by isomorphisms on S. So this would be morphisms from E to Q. And then we define the K theory space. It's actually a spectrum in the sense of homotopical geometry by taking the classifying space of Q1 X and looping this out once. So in homotopy theorem, you use the script K for the spectrum. Then the usual Ki of X would be the isomotopy group of this here. So that's kind of the definition of K-theory, and I want to explain a few results on that. I mean, it's a very abstract definition that's hard to handle. You can compute for monoid schemes, things are better computable than for usual schemes because they're very simple. Um, I mean, its topological spaces are finite. We've seen that, but it's easier to compute with than in usual algebraic geometry. But I just want to show you some general theorems. So the first one is actually what Soleil proposed is true. So this is actually here. I'm almost done. It's the last couple of slides, so I don't go much over time here. So Soleil's prediction Ki of F1 should be the stable homotopy groups of the spheres. With this definition, it becomes a theorem, and this is something that Deitmer actually did. He set up K-theory for monoids, not for monoid schemes, but just for monoids, and he showed that this is true. So somehow it's funny. We used now a very different definition than this BGL infinity in the beginning, but still it works out. The prediction of Soleil is true, which is a good thing, which shows somehow coherence here. Come back to this in a moment. I worked then later with Chenghao Chu and Rekha Santanam on extending this to K-theory of F1 schemes, and we strengthened that to an identification of spectra. So the spectra of F1 is homotopy equivalent to the sphere spectrum. And actually, I mean, we defined the K-theory spectrum of any monoid scheme, and we show that the Q construction actually is equal to the S construction. So this is, I don't go in here in detail. If you know that, this tells you something for usual scheme. The Q construction is equal to the S construction, and this also works in this context, even though we don't work with exact categories anymore. Okay, and then a little later, this was a few years ago, I worked with Jens Eberhard and Matt Young on K-theory of monoid schemes, and we got kind of significantly stronger results on that. So this is mainly in the integral case. Well, a little more general, but let's say integral. Well, A is integral if it's something like an integral domain. And the right way to say this, well, classically an integral domain is a subring of a field. An integral monoid, it's a submonoid of a group. Well, we have to exclude the zero. But the non-zero elements form a submonoid and it embeds into a group. And then monoid scheme is integral if and only if all coordinate algebras of local sections are integral. And under these assumptions, X being integral, first of all, we the K-series spectrum is equal with the plus construction. So this here is the plus construction, another construction of K-theory. Namely, this is abstractly really easy to say. We take the maximal group root of our category of vector bundles. So it's the same objects and just isomorphisms. We forget about other maps. And then we localize the category and take the classifying space. So yeah, in a sense, conceptually, it's much easier to define it like that. Yeah, I don't know. I'm not a super expert on K-theory, so I don't know the advantages and disadvantages of these different approaches. But the plus construction, that's fairly easy to the GLN description that we started with, which is maybe the most explicit construction of K-theory. But this is the other theorem that we have. If X is integral and A are the global sections of X, so if X is affine, X would be the M spec of A, but if X is not affine, A is something else, then the K-series spectrum can be expressed in terms of GL infinity of A. So more precisely, it's a direct sum. Direct sum means you have point topological spaces. So in almost all factors, we have the base point, and finally factors, it's something else, which is indexed by elements of the Picard group of X. And then we have a factor Z. It's just Z just means it's a discrete topological space of countable cardinality times the classifying space of GL infinity of A plus with the base point. And GL infinity of A here, I wrote this down, but the definition is what's below. You should think of it as generalized permutation matrices. So permutation matrix where your coefficients are elements in A, invertible elements in A, but which is the identity matrix up to finitely many coefficients. And abstractly, it's a Rath product of the units of A with S infinity. So, I mean, we don't need this matrix interpretation. It's just an abstract group. And this now realizes Soleil's initial definition that was in red. So in case that X is affine, so if X is a spectrum of A, then the Picard group here is trivial. That's for monoid schemes. Monoids are all local in a sense. So they cannot have a non-trivial Picard group. Class number is always 0. So what happens is that this part here is gone. And then our K-theory spectrum, well, this is factor Z. So there are infinitely many copies of that. And then we have B of GL infinity of A plus. So in a sense, after a long tour of theorems, we come back to Soleil's original definition, which was somehow not so clear. I mean, for F1, he had a definition, but was not so clear how to generalize that, because for rings, it's a little subtle, but you just use the easiest definition possible. And you get this description of K-theory that Soleil was wondering about. It is generalized actually to arbitrary monoid schemes. Okay, so this is kind of an overview of what's known about K-theory for F1 geometry, and I hope a little bit that this is helpful. I think that's all that I want to say. Thank you.
Thank you very much, Oliver. Uh, so any questions or comments? Maybe I will ask one question about you defined schemes over F1 as some sort of monoidal scheme, right?
Yes.
Uh, do we have zeta function for these schemes over F1?
Yeah, for monoid schemes, the zeta functions are, if they have torsion, it's a little complicated. But let's say in the toric case, if the monoid schemes comes from a fan, then yes, because the toric variety decomposes into torus orbits, and for that we have counting polynomials. If there's a torsion, like if our monoid is something like Z model or N, then there are problems if in characteristics that divides n. So there are certain things that don't work. But in essence, if we have a nice variety which doesn't have weird geometric properties, something that we would like to define as a variety like over a field, it has a zeta function.
Thank you. Uh, any more questions or comments? Do we have some sort of motives over F1 kind of thing? Grothendieck's theory of motives over F1.
Mhm. Yeah, there's not much developed. There's a paper by Yurimani and Mathilde Macaulay where they go in this direction. But I mean, there's little developed. I think there's no really obstacle to go in this direction. Um, but it's also not so clear where we should go. Well, it's a matter of motivation. So I think for one geometry, there's two main streams of motivations. One are these arithmetic applications that I mentioned in the beginning, and there are people working on that. They're highly interesting, but they're also very difficult. And as far as I know, there is no real application yet. And there kind of connections to combinatorics, which is very successful. And there are a lot of things that have been done that work. And motives is I have this one. I should say there's one with really important work, which is by Jacques Weibel and Christian Haselmeier and who was the others? Christian Cortines? No, Christina Cortines and someone else who used monoid schemes for CDH descent. And I mean, this is very much related to motivic homology. This appears there. So they used monoid schemes to study CDH descent, I think, for toric varieties, also a positive characteristic. So there's a strong link, well, to motivic homology, not to motives directly.
Thank you. Uh, any more questions or comments? So let's thank Oliver once more. Yeah. So most probably this is our last seminar talk for this term. We will continue in the fall term of 2025. So end of the summer. We all thank for all of the speakers and participants and hope to see you within 2 or 3 months' time. Yeah. So bye bye. See you all later. Thank you.
Thank you. Bye bye.
Bye.